Hello everyone and welcome to Control Engineering and Control Theory tutorials. In this tutorial, we provide a concise explanation of external and internal input disturbances in control systems. And here's the motivation. Our experience, as well as experience of our colleagues, shows that a large number of people, as well as engineers, do not properly understand the main philosophy of modeling disturbances in control systems. For example, as you will see in this tutorial, there is a school of thought in control theory that sees disturbances not only as external, uncontrollable inputs that affect the dynamics, but also as model uncertainties. This is probably unknown to a large number of people outside of the research community. The disturbance modeling is extremely important. Namely, once disturbances are properly understood and placed in the appropriate control engineering modeling framework, we can use a number of methods for disturbance control and attenuation. However, to be able to identify the appropriate control method for suppressing disturbances, it is of paramount importance to properly model them and to properly understand them. But before we start with explanations, here's the copyright notice. This tutorial, web page, video lesson, developed code files, and documents following this tutorial should not be copied, redistributed, or posted on public or private websites, public or private code repositories, or social media platforms. This lesson and all the provided study materials are strictly for personal use. Without the permission of the author, that is, without permission of Aleksandar, Haber, this lesson and the provided material should not be used for commercial purposes and for training of engineers working in companies. Then, this lesson and the provided material should not be used as lecture materials on online learning platforms and the official university courses. Then, this lesson and the provided material should not be used to train an AI algorithm or a large language model. Without the permission of the author, the provided code files should not be used for academic research or for commercial purposes. First of all, let's revise the classical feedback control system structure. If you open any book on control engineering, you would often see this block diagram. Here in this block diagram, S is the complex Laplace domain variable, that is, this is the representation of the system in the complex Laplace domain. C of S is the transfer function of the controller, that is, this block over here represents the controller. Then P of S is the transfer function of the plant. Then R of S is the reference signal and Y of S is the output. E of S is equal to the difference between R of S and Y of S, and this is the control error. F of S is the control input to the plant, and D of S is the disturbance. The goal of the control algorithm is to make sure that the output Y of S tracks the reference signal R of S despite the negative effect of disturbances D of S. What is often missing in control engineering book is the proper explanation of the disturbances D of S. Namely, usually the authors of popular books will simply run over the disturbances D of S. However, as you will see in this video tutorial, disturbances are very important for proper modeling of control systems. There are several types of disturbances. In this video tutorial, we will focus on the input disturbances. Briefly speaking, input disturbances can be divided into two branches. We have the external disturbances and we have the internal disturbances. Let's start with the external disturbances. External input disturbances are external inputs that affect the dynamics of the system or plant dynamics and that are not created by the controller. So carefully listen this statement. Again, external input disturbances are external inputs that affect the dynamics of the system or plant dynamics and that are not created by the controller. If you now look at this block diagram, you will see this control input over here, which is an input itself. However, this input is determined by the controller, and we have complete control of this input over here. However, there are also inputs that affect our dynamics and that are not determined by the control algorithm. And these inputs are called the external input disturbances. The external input disturbances are usually not known, or we only have limited knowledge about certain aspects of external input disturbances. For example, we know that the input disturbance is a sine signal of a known frequency, or we know that the input disturbances are, for example, equal to a colored noise, or can be modeled as a random process with a colored noise properties. That is, we know the covariance matrix and we know the mean of the input disturbances. However, we don't know the practical or a particular realization of input disturbances. Sometimes we don't know anything about input disturbances. What is very important to keep in mind is that we are not able to actively control external input disturbances at their source. That is, we cannot put some controller at this point over here and simply reject the disturbances. The disturbances are always rejected implicitly through an action of the control algorithm. However, they still somehow affect the system. And here is a practical example of external input disturbance. What you can see over here is a mass spring damper system. We have a box with a mass of m, we have a damper with a damping constant kd, and we have a spring with a spring constant ks. Over here, this force F of t is exactly this force over here, only the force over here is in the time domain and the force over here is in the Laplace domain. That is, this is the force that's being exerted by the controller on our mass spring damper system. And over here, we have the disturbance force. This disturbance has a unit of force, and this is the action of the environment on our mass spring damper system. For example, someone can hit the mass with a hammer, or there's some external vibration affecting the mass motion, or maybe this whole system is sitting on some vehicle and vehicle accelerates and deaccelerates, and then these acceleration and the acceleration can be modeled as inertial forces, for example, or a similar type of modeling. In this particular case, the control objective can be to control the position of the mass, where the position or the displacement of the mass from its equilibrium position is denoted by y. Besides external input disturbances, we also have internal input disturbances. And before we state a formal definition of the internal input disturbances, let's first give this example. Let's again consider our mass spring damper system. And if we write a second Newton's law, we will obtain this ordinary differential equation that describes the dynamics of the mass spring damper system. In this differential equation, Ks is the spring constant, Kd is the damping constant, m over here is the mass, F is the control force, and d is the disturbance. Now, we will call this model as the true model. That is, we will assume that this model accurately represents the physical reality. That is, that the system is exactly linear and that it behaves according to this equation. Now, we as modelers never know the exact or true model perfectly. There are always model uncertainties. To follow this line of thought, let's assume that the person modeling the system assumed that the model looks like this. That is, the person modeled the mass, modeled the spring, modeled the external force, and modeled this disturbance d of t. However, this person omitted the damping term. That is, he or she omitted this term over here. Then, after model validation experiments, the modeler realized that the model is not accurate. Namely, every time you build a model, you want to make sure that this model represents the physical reality. And consequently, you will spend some time validating this particular model. That is, you will see how well this model represents reality. How this thing is done? Well, you're going to perturb the real system from its initial condition. That is, you're going to simply move mass left or right, and you're going to let the mass to oscillate. And then you're going to record output y. And this time series will be used for validation. Then what you will do, you will take this differential equation, you will set the same initial condition that is equal to the initial condition that's used to simulate your system, and you're going to solve this differential equation, and you're going to obtain the simulated y. Then you're going to compare the simulated y and the experimentally measured y, and you will see how far is your model prediction from the true system. Based on this information, you can argue about the validity of this model. What will happen over here with this model once a user starts to simulate this model is that you will see that the oscillations are not being damped. This is because the model is missing damping over here. However, over here, due to the damping, the oscillations will die over time. Now, our modeler, that is, he or she realized that, and to compensate for this model uncertainty, he or she can include an extra term over here that I denote by d bar. Maybe you don't see bar over here, however, there is this term d bar, and you can see it better over here. Now, from the true model, it follows that the extra disturbance term is actually the damping term. Namely, if you take the original equation given over here, and if you move the damping term over here, you can see this damping term as this d bar over here. That is this term. And in this way, we can actually model uncertainties as disturbances. That is, as internal disturbances affecting our system. That is, this disturbance over here, d bar, is the internal input disturbance. The internal input disturbance, that is this term d bar, does not originate from a physical external force affecting the dynamics, but it originates from our lack of knowledge of the system model. And this is the main idea of introducing internal disturbances. Again, to repeat, internal disturbances are not physical forces that exist in the system. They're actually are modeling uncertainties that a modeler takes into account and includes these disturbances in the model to compensate for our lack of knowledge of the exact system model. And it's always advisable whenever you model a system to include this extra disturbance term. Maybe this extra disturbance term is a colored process. That is, maybe it has some correlation function, and you can exploit this correlation function to improve your model later on. This particular form of internal input disturbances comes from the lack of knowledge of the model structure. The model structure is the mathematical form of the model that includes all the terms, derivatives, and constants. And let's go back to our example. Over here, we don't know the model structure. This is because we have omitted the damping term. However, there are also internal input disturbances that originate from the lack of knowledge of the model parameters, or to be more precise, the lack of knowledge of the numerical values of the model parameters. And let's illustrate this with the following example. First of all, let's assume that the model structure of the system is known accurately. That is, our modeler knows that there is an acceleration term, damping term, spring force term, external control input, and this external input disturbance term. However, our modeler does not know the precise values of the mass, damping constant, and the spring constant. In fact, the modeler knows only the nominal values represented by these bars over here. That is, the modeler knows M bar, Ks bar, and Kd bar. Let's explain all the terms once more. In this equation over here representing the true model, M, Ks, and Kd, that is M, Kd, and Ks, are the exact values of the model parameters that match the physical reality perfectly. These values are called the true model parameters. The true model parameters define the true model of the system, which is almost never known exactly. Then, over here, we assume that the true model parameters are equal to the nominal model parameters, which are known to the model designer, and these terms over here representing the modeling uncertainties. Consequently, M bar, Ks bar, and Kd bar are the values of the model parameters that are used by the modeler and control system designer. These parameters are usually called nominal model parameters or nominal parameters. The nominal model is determined by the nominal parameter values. That is, the nominal model is the model that is known to the system modeler and control engineer, and the nominal model is used to design a control algorithm. In fact, the true model is never known exactly, and we only know the nominal model parameters. That is, we know M bar, Ks bar, and Kd bar. Delta M, delta Ks, and delta Kd are model uncertainties. That is, these variables represent a mismatch between the true and nominal model parameters. That is, they represent the mismatch between the true and nominal models. Now, if we substitute the expression for M, Ks, and Kd given over here in our true model, we will obtain this equation over here. For example, instead of M, we can write M bar plus delta M, and everything stays the same on the right hand side. After rearranging the last equation, we obtained this equation over here. So what did we do over here? We took all these uncertain terms, such as delta M multiplying acceleration, delta Kd multiplying velocity, and delta Ks multiplying y, and we put them on the right hand side of the equation. Then, we can define the internal input disturbances d bar by taking these parameters, multiplying the acceleration, velocity, and displacement, and we can group them together and we can call them as d bar. And d bar is now the internal input disturbances. Consequently, our dynamics can be written in this compact nominal form, where on the left hand side are the things we know. Then on the right hand side we have the force F, and that's our control force. Then we have the external input disturbances, which are not known, and then we have the internal input disturbances represented by this term d bar. The system modeler and control engineer can now work with the nominal model parameters M bar, Kd bar, and Ks bar, and they can consider the model uncertainties as disturbances. Again, the model uncertainties in this representation are considered as disturbances. And this is a very important technique in control design philosophy, in control engineering, that is the basis of robust and data-driven control approaches. From the previous example, we can conclude once again that internal input disturbances can also originate from the lack of knowledge of the values of system parameters and not only from the lack of knowledge of the system structure. Another important thing to observe is that the internal input disturbances affect the nominal plant dynamics. That is, they are not physically present in our system, they originate from our modeling approach and the simplifications of the system dynamics. In fact, one can argue that every model is not an exact model, and that's why it is a good idea to include disturbances in our model to take into account unmodeled dynamics. That is, in a number of control engineering approaches, when you see a disturbance term, this disturbance term can also originate from model uncertainties. To summarize and to define the internal input disturbances. The internal input disturbances are inputs that affect the nominal plant dynamics and that take into account our lack of knowledge of the numerical values of the model parameters and the lack of knowledge of the model structure. And that's all for today. Thanks for watching.